So example 4.2.2, calculating theoretical probabilities. So suppose you conduct an experiment where you flip a fair coin twice. So flip a fair coin twice. So this is our experiment. And part A says we want to list a sample space. Now, to be able to do theoretical probabilities, we need the sample space to have equally likely outcomes. So we need the sample space to have equally likely outcomes. So if we have a fair coin, that means each side is equally likely to occur. But we're not just flipping it once. So it says that we're going to flip it twice. So for equally likely, outcomes, since we already started with equally likely for each side, if we want to hold on to that equally likeliness, we need to consider all possible orders of the flips. So for equally likely, we need all possible orders of the two flips. Alright, so for this one, for our sample space here, the first flip could be a head, and the second one could also then be a head. Or the first flip could have been a head and the second one a tail. Or the first one could have been a tail and then a head, or a tail and a tail. Now, if we were going to consider a lot more flips, we would come with a more systematic way, like through tree diagrams, to do these, which some of you may have seen. So like the first flip could be either a head or a tail, and the next flip could either be a head or a tail. And then if we trace out from our start all the paths, we have HH, HT, TH, TT. Okay, but again, we're going to get back into things very quickly after this chapter to how they deal with data, in which case we're not going to be looking at these tree diagrams and listing out of sample spaces because they're going to be too large to list. Okay, but in this initial chapter we're going to start with these small sample spaces to get some idea of what's going on with these probabilities. So part A, we were asked to list a sample space. And since we're dealing with theoretical probabilities, we do want one that has all equally likely outcomes. All right, so then the next one asks us for the probability of getting exactly one head in that flip. Okay, so here's our probability of, and then usually what follows those words then is our event. Okay, so our event, we call event A, some capital letter, is going to be getting exactly one head. So that's what we're going to let that variable be equal to. And so then our event space so the set that corresponds to that is we go back up to our sample space and we list everything that meets this condition. So getting exactly one head. Okay, so the first outcome is HH, so we got two heads. That's not exactly one. The next outcome was HT, so there we did have exactly one head. The next outcome was TH, again we got exactly one head. And the last outcome was tails, tails. We didn't get any heads, so again that does not meet the condition of getting exactly one head. So our event space has these two outcomes in it, HT and TH. So now, probability of A, we're going to count up the number of things in the event space, which is 2, and divide by the total number of things in our sample space, which was 4. So 2/4, or we could write that as 1/2, we could write that as 0.5, or we could write that as 50%. Okay, all 4 of those answers are correct. Okay, so any one of those would be counted as a correct answer. Okay, and this was using the equally likely rule. So again, if we can list a sample space of all equally likely outcomes, then probabilities really just become two counting problems that we put together into a fraction. So the numerator, we counted the number of events here in the sample space that met our condition of getting exactly one head. And that became our event space here, those actual outcomes. And then the denominator, we just counted the total number of outcomes in that sample space. So looking through this sample space, there's 2 out of 4 of those outcomes that meet our condition. So the probability of A is 2 out of 4, or 1 out of 2, or 0.5, or 50%. So part C, we want the probability of getting at least one head. So this is the event that we're interested in now, is getting at least one head. So let's let, and again, the letter we use doesn't matter here, so I used A on the last one, so I'm just going to use B here. So we're going to let B be the event of getting at least one head. So then our event space that corresponds with that, if we go back to our sample space, so getting at least one head, the first outcome we had was HH. So let's also write in here at least one. That means one or more. So that first outcome, HH, 2 heads, so that's at least one, that's one or more. Okay, and then we had HT and TH. Okay. So there were 3 different outcomes in the sample space that met the condition of getting at least one head. So our event space B has 3 outcomes in it. So now that means that the probability of something in this set happening is 3 chances out of 4, or 0.75, or we could write that as 75%. And again, this was using the equally likely rule. Part D asks us for the probability of getting a head and a tail. So again, here's these words, probability of, so our event, in this case that we're interested in whether it happens or not, is getting a head and a tail. Okay, so we're going to let our event C be getting a head and a tail. Now here it's important that we flip the coin twice. If we flip the coin once, the chance that we would get a head and a tail on one flip of the coin would be 0. That would be an impossible event. But in this case, we want any of the events where we saw a head and a tail. It does not specify which order those can happen in. So our event space C, we need all of the outcomes where we had a head and a tail. So that would be HT and the outcome TH. So now the probability of event C happening would be 2, because there's 2 things in our event space, out of 4 in the sample space. So again, we could also write this as 1/2, or 0.5, or 50%. Okay. We do not need all 4 of these answers. Okay. Any one of those answers would be correct. And again, this is using the equally likely rule. So again, it's really important in the very first step that we had listed all the possible orders that the H's and T's could happen, so that we can use the equally likely rule to compute these theoretical probabilities. All right, so part E says, what is the probability of getting a head or a tail? Okay. All right, so or means at least one of these happened. So in here, we're going to let D be the event of getting a head or a tail. And up here we should have emphasized here, and means both of these happened. So every event we listed here had a head and a tail. Okay, now we just need at least one of those to have happen. So as we're listing out our event space, first outcome in the sample space was HH. So did we get a head or a tail here? Yes. Okay, we had a head right away on the very first thing, so we just need at least one of these things to happen. Okay, the next outcome we had was heads, tails. So again, we just need at least one of these things happen, so we need a head or a tail somewhere to have happened, which they did. Same thing with tail head and tail tail. Okay? So all of the outcomes meet, every time we flipped the coin we had to have flipped either a head or a tail. Okay, so in this case our probability of this event happening is 4 out of 4, or 1, which is 100%. It has to happen. Okay? And again, I just want to keep emphasizing that in these cases we are using this equally likely rule, which allows us just to count events. Okay, later we aren't going to be able to do that when things are not equally likely. All right. Part F says, what is the probability of getting a foot, which doesn't even make sense for this particular problem. So in here we're going to let E be the event getting a foot. The authors had to come up with something kind of crazy for this one that absolutely can't happen. Okay, so in this case our event space E is what we call the empty set. Okay, so we've got the set notation with nothing in it. Okay, so in this case the probability of this event happening, there's 0 chance out of 4. Okay, this absolutely can't happen. If we flip a coin twice, we're not going to get a foot. That's just even weird to say out loud. Okay, so again, 0% chance. And then part G says, what is the probability of each outcome, and what is the sum of these probabilities? Okay, so sum is a word from mathematics that means this is the result of addition. Okay, so the answer to an addition problem. So the probability of each outcome. So let's just go back first and just relist the sample space. So we had H, 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 T, T, H, T, T. And we want the probability of each of those. So the probability, since all of these were equally likely, because we had a fair coin and we considered all possible orders, all 4 of those probabilities is the same. And HH is in here 1 out of 4 times, HT is in here 1 out of 4 times, TH is in here 1 out of 4 times, and TT is in here 1 out of 4 times. So they each have a 1 out of 4 chance of happening. And if we compute that sum then, that sum would be 1/4 plus 1/4 plus 1/4 plus 1/4, should be 4/4, which is back to 1, or 100%.